finish up our study of Chapter 8 in Section 8.3, which is Derangements. Nothing is in its right place. So a derangement is essentially a permutation with no fixed points. And here's what I mean by that. Let's take a look at the example because it will make it very clear. Say you have 3 people at a so-called party. I'm not sure I would call that a party. Each person threw their coat on the bed. When the party is over, everyone picks up their coat at random. What are the chances that nobody gets their own coat? So again, we're looking here at probability, which we haven't done much with in this course yet. So if I'm talking about chances, then I know that my denominator is going to be the total number of ways that it could happen, and the numerator are the number of ways that satisfy the condition. So in this case, my total number of ways, because I have 3 people at a party, is going to be 3 factorial. Because once the first person has 3 coats to choose from. The second person only has 2 coats to choose from. The third person only has 1 coat to choose from. That's 3 factorial. The numerator is a little bit more work, or a lot more work. In this case, just a little, because we're looking at 3 people. So let's look at the brute force method before we look at how we can use our principle of inclusion and exclusion to help us. What we're looking at here is that nobody gets their own coat. That nobody is what makes it a derangement. Derangement is saying there are no fixed points, which means person number 1 must either get coat 2 or coat 3, either one. Person number 2 has to get coat 1 or coat 3. Person number 3 has to get coat 1 or coat 2. And again, these can be in either order. You get the idea. Now, let's not get confused with the table I made down here. What I'm looking for is, what's this number? What are the number of ways that nobody gets their own coat? So if you'll notice, for person 1, I've randomly said in the first trial, you're going to get coat number 2. Well, if person 1 gets coat 2, then person 2, I can't give them coat 1, because if I did, person 3 would get coat 3, and that's not a derangement. So if you'll notice, there's only one way for this to happen. If person 1 gets coat 2, then person 2 has to get coat 3, and person 3 has to get coat 1. Same thing if I set person 1 to coat 3, then it must be that 2 got 1 and 3 got 2. So really, I've already exhausted my list. There's 2 ways out of 6, or 1/3 of the time, we're going to have people that where 1/3 of the time nobody is going to get their own coat. Now, this was not horrible because we had 3 people, but let's say now you've got more friends and you have 10 people and 10 coats. Well, that's going to make things a lot more difficult, because it's not going to work out so nicely here in my little table where if 1 gets 2, then 2 must get 3, etc. There's going to be a lot of different ways that that can happen. So let's look at a mathematical way to go about this. So try not to cry when you look at this slide, but let's take a look at it. This is 10 people, and we're looking at the derangement where nobody gets their own coat. So 10 people, 10 coats. Now, we don't want to make a table. That would be stupid. Let's instead take a look at the principle of inclusion and exclusion. Now again, the way that we write this, the way that we write our conditions, is really key. Because if I'm trying to find where nobody gets their own coat, and I know the principle of inclusion and exclusion says not C1, not C2, etc., then I need my condition itself to be that each person gets their coat. So remember, when we talked about section 8.1, we said it always has to be the opposite, because the principle of inclusion exclusion is going to give us the not. And again, I've just rewritten the formula so that we remember what that formula was. And then I just started finding those values. So again, just like we did before, S0 is essentially the sample space. There are 10 people. So the first person has 10 codes to choose from, the second has 9, etc., all the way down to the last person who's left with whatever code is left. So there's 10 factorial total ways. For one person to get their code, that means that the first person got their code. Now there's 9 people left, so the next person has 9 codes to choose from because one already got his or her own code. The next person has 8, etc., all the way down to 1. So again, that's 9 factorial. Now, where does this 10 choose 1 come from? Because there are 10 conditions, and I'm choosing one of the conditions to be met. And we can see what this pattern is going to do. 10 choose 2, 10 choose 3, 10 choose 4, etc., all the way to 10 choose 10. And the number of codes left keeps decreasing because we're setting more and more codes equal to the correct person. Now, from here, I really just did some math to simplify. 10 choose 1 is the same as 10 factorial over 9 factorial, 1 factorial. 10 choose 2 is the same as 10 factorial over 8 factorial, 2 factorial. Now, why did I do this? Well, because I did this problem ahead of time, and I know what's going to happen is I'm going to end up with a handy-dandy little cancellation that's going on. Now, again, that leaves me with this expression. Now, what did I do here? I said, oh, look, everything has a 10 factorial on it, so let's factor out the 10 factorial, and now I've got 10 factorial times all of this. And typically, I'm not looking for the actual number, but in this case, I'm going to go ahead and find the actual number, which the total number was 1,334,961. And again, I'm looking at chances, not numbers. So if it said what is the number of ways that could happen, I would be done. Because it says chances, I need to take it divided by the total sample space, which is 10 factorial. When I divide that, I get about 0.368. Now, that's a pain, right? That's a lot of work. It's a lot of math. It's a lot of different places I can make a mistake. Let's take a look at if I'm okay with an approximation of this value. So for our 10 code example, after we did all of that math, we came up with 10 factorial and then 1 minus 1 over 1 factorial plus 1 over 2 factorial, etc., which came up with this number. And in general, again, we were looking at where this is an n. So I said in general, and then I made it for 10. This was n minus 1, this was n minus 2, this was n minus 3, etc., all the way down to n minus n factorial. So that's sort of the generalization, which can be written in a more succinct way like this. And we've talked about how to go from writing a sequence or series into writing it in summation notation. Remember, this -1 to the k just changes this sign from plus to minus, etc. And the k is the number of favorable, so 1 condition met, 2 conditions, 3 conditions, etc. That's where that number will come from. And then n minus k is where we came up with the n minus 1, n minus 2, etc. Now, someone much smarter than you or I noticed, as they did more and more derangements, that the derangement was equal approximately to n factorial divided by e, the natural exponential function. So if I, in my calculator, take, in this case for D10, 10 factorial divided by e, I come up with this value, and guess what this value rounds to? Oh, about the same thing. In this case, it is the same value. But again, it might have rounded differently, which would have made it an approximation, but essentially, this is what we're looking at as a great approximation for D10. So let's take a look at just a quick example, which is basically the same thing as the coat question. This is talking about different gifts, but could I just cross out gifts and put coat? Yes. 10 turns into 14. If I want the exact number, I'm finding D14, which is 14 factorial. Remember, that's where we took that value and factored it out. And then the summation from 0 to 14 of -1 to the I over I factorial. And again, could I write this out? Yes, but I don't want to because that would be silly. Approximately, it's just 14 factorial divided by E. So I have two questions for you to try, and in those two questions, they are going to make you think a little bit. They're not going to be straightforward. So I want you to pause, try both of these questions, and when you're ready, press play to see how you did. I will go ahead and give you a hint for each one, and then we will go through these together. So first question. The essential question for both of these is that you have 12 women going to a party. They're turning in both their purse and their keys separately. And the first question I'm asking, in how many ways, so again, we're not talking probability, but in how many ways can no woman get the correct purse or the correct keys? Which means it could be they get one but not the other, etc. So what I want you to think about is that we have two events where no women get their own coat, and then we have no women get their own keys. Those are the two events. Well, when we have two events, we're just going to multiply, and this is a straight up derangement. Nobody gets their own coat times nobody gets their own keys. D12, D12, using that approximation, we're saying 12 factorial over E twice because there's coat and keys. For the second question, in how many ways can the women leave the party so nobody gets back both their keys and their purse? So now I'm saying I'm leaving the party, I've got somebody else's purse, I've got somebody else's keys, and everybody else at the party, same thing. So I don't leave with any of my own possessions. Now this one's a little bit different because we're instead going to think about the fact that our condition is that condition 1 is that woman 1 gets both her purse and her keys. And so this is not a derangement, this is just principle of inclusion exclusion. We're saying, hey, let's start with the full Monty, right? Start with everything, which is the sample space, 12 factorial, and then use the principle of inclusion exclusion. And again, notice I'm squaring it because I'm saying essentially that two events are happening. So I would end up with the summation from 0 to 12 of 12 choose k, 12 minus k factorial, quantity squared. Last question for you to try, which is number 12 in your textbook in section 8.3. Miss Pizzullo is teaching geometry and then biology to a class of 12 advanced students in a classroom with 12 desks. In how many ways can she assign the students to those desks so that A, no student is seated in the same desk for both classes, or exactly 6 occupy the same desk for both classes? So let's start with the easier one, and again, feel free to pause and try these questions first. I encourage you to do so. But for A, we're looking at no student is seated at the same desk for both classes. So this is very similar to the first question on the last page. Essentially, I'm saying it's a derangement with 12 items, and it's happening not twice though, because the first time that the students come into the room, do we care where they sit? Nope. How many ways can they sit? 12 factorial ways, because the first student has 12 desks to choose from, the next student that comes in has 11 desks to choose from, etc. So this is the first class. There are 12 factorial ways to arrange those students, and we don't have to worry about the derangement yet because we haven't assigned a student to a desk yet. Now, the second class, now we're talking about D12. D12 because I'm saying I've already assigned them now for the first class. For the second class, I want them to be all in different desks. So 12 factorial times D12. Again, I'm using that approximation for D12, which is 12 factorial over E. So here's my final estimated solution. For B, Exactly 6 students occupy the same desk for both classes. So again, I'm going to start it the same way, but now I'm looking at essentially a derangement of 6. So 6 of the items cannot be in the same place. So again, I'm going to use 12 choose 6 because I'm choosing out of the 12 students, I'm choosing 6 kids, and I'm saying none of those 6 kids can be in the same desks as before. So 12 choose 6, 6 factorial over e. Again, I could continue and simplify this. I could write it just like this, or I could continue to simplify. Either way, that's going to be the correct solution.